Hello everyone, welcome to this presentation entitled Effect of EMI filter on the dynamic response of DC-DC converters. This is a very relevant topic that many times is neglected in basic courses on power electronics. So in this video we will see an introduction, then we will see how to obtain the open loop control to output transfer function considering the EMI filter. We will see also how to calculate the control to output transfer function including the EMI filter. We will do a study of stability, and along this video we will see an example and several LTE SPICE simulations to support the different analysis. These are important videos related to this topic, Power Electronics number 3, ultra-fast modeling of DC-DC converters. We will be using some of the results obtained from this video, and LTE SPICE 24, which shows how to obtain the loop gain of a DC-DC converter by simulation. If you like this channel, please remember to subscribe. Here on the left we can see the typical schematic of a DC-DC converter. For example, in this case is a buck converter that we know very well. But in reality, we know that if the input voltage comes from a DC grid, we are going to inject into the grid pulsating current as shown here, because this is the current that is circulating through the switch. So this current is nearly a square waveform, so it's going to have a lot of harmonics, and then we know that we will be injecting all these harmonics in the grid, and this can cause problems in other systems and also noise and many different issues. So we also know that we are going to require in many applications the use of an EMI filter. So we usually place a filter like this with an inductor and a capacitor. So in this way we can filter the current circulating through the switch, so that the current that is drawn from the grid is almost a DC current. However, it can seem that the placement of this LC filter here is something innocent, just two passive elements before the main DC-DC converter, but the reality is that these elements, this EMI filter, is going to affect a lot the dynamic response of our DC-DC converter. So usually we are going to have to take into account the effect of this EMI filter on the dynamics of our DC-DC converter. Otherwise, we can get unstable operation, or at least not the operation that we were expecting. So let's investigate a little bit further. Let's start by remembering what we have seen in this video, Power Electronics number 3. We model the buck converter in continuous conduction mode using the average circuit in continuous conduction mode, using the average current through the switch, the average voltage across the diode, and all the different elements. So in this circuit, we know that everything is average within the switching period. And from this circuit, we obtained the small signal circuit of the buck converter in continuous conduction mode by taking perturbations and using the Laplace variable. So we obtain this small signal circuit. And from this circuit we can obtain all the different transfer functions that represent the dynamic behavior of the converter. So let's consider now what happens when we add the EMI filter at the input. In order to consider the EMI filter, we only have to add the two elements at the input of the buck converter, of course. So in the average circuit, we have the same situation. We add these two elements into the average circuit. We have to pay attention here because now this voltage source, for example, here is the duty cycle times the input voltage, but now the input voltage is the input at this point, so is the input across the filter capacitor. So again, we can apply the small signal analysis by introducing perturbations and using the Laplace transform. So because at the end we are adding these elements here which are linear, the small signal circuit is just the same circuit but adding here the passive elements in the Laplace domain. Again, taking into account that this voltage source here depends on the voltage across the capacitor. So now we have this circuit, and from this circuit we can get any of the four transfer functions that we can obtain to define the dynamic behavior of the converter, the input impedance, the output impedance, the control to output transfer function, and the audio susceptibility transfer function. Today we are going to focus only on obtaining the control to output transfer function, including the EMI filter and also the loop gain of the converter in closed loop in order to analyze the stability. So let's start by this control to output transfer function. We know that for this we have to make null the perturbations on the input voltage coming from the grid. So we get this circuit here. This is a rather complicated circuit, so we are going to simplify the analysis by defining this impedance here, ZF, which is the impedance of the EMI filter of both elements in parallel. And also we are going to define this other impedance here, ZP, which is the parallel combination of these two impedances, and also the impedance of the inductor ZL. So with this we are going to be able to obtain simplified transfer function for the control to output behavior. Here we have the definitions of the three impedances. Using the Kirchhoff laws we can get these equations, and from them very easily we can get finally this expression here of the output voltage over the duty cycle, which is the control to output transfer function. And all this is very convenient because it's very simple to represent, and we can use all these equations in our WinPython script to obtain the behavior of the converter. Also, this is interesting because we can have a particular case if we want to obtain the response of the converter without EMI filter. We only have to make ZF equal to 0. So then we get this expression here for the control to output transfer function without EMI filter. So we have with this, we have everything for comparison of the behavior with EMI filter and without EMI filter. We are going to use the same converter that we have seen in previous videos with an input voltage of 10 volts, an output voltage of 5 volts, 1 ohm of load resistance, and these are the different parameters of our converter. This is the output voltage, and now we need to calculate the values of the EMI filter that we are going to use in our converter. So for this we are going to consider this part of the converter so we can get this equivalent circuit at the input. Considering the AC operation, the DC input voltage is a short circuit. Here is the current through the switch. So we can analyze this circuit. We can obtain the different harmonics that we are going to have at the input. for the different harmonics of the current through the switch. We can analyze this circuit and obtain these equations here that finally provide us with the amplitude of the different harmonics of the current through the grid as a function of the different elements, operating frequency, and amplitude of the corresponding harmonic of the current through the switch. So here we have more information about how to calculate the values of the EMI filter. This is the response of the EMI filter, the current through the grid over the current through the switch for the different harmonics. So this is a second order response, and usually the way to calculate this is to place the cutoff frequency of the filter low enough to have a good attenuation of the different harmonics of the current through the switch. So we can select, for example, a value of the cutoff frequency between 1/10 and 1/100th of the switching frequency. Then we select a suitable value for the capacitor CF and obtain the value of the inductance using this equation. For example, in our case, we have taken a value of CF of 10 microfarads. The switching frequency is 200 kilohertz. So we have selected the cutoff frequency of the EMI filter equal to 5 kilohertz, and with this the value of the inductance of the filter is equal to 100 microhenry. We can do a simulation of the converter to check the behavior of the EMI filter. So here we have our converter, our buck converter operating in steady state, and here we can see the output voltage in blue, so it's 5 volts. This is the input voltage in green. And at the bottom we can see the current through the switch, which is the pulsating waveform, and then we have the current through the grid, IDC, which is here in red, and we can see that it has a very low ripple, so it's almost a DC current circulating through the grid. So now we have already our EMI filter. Let's see what is the effect on the dynamics of our converter. First, we can plot using this WinPython script both transfer functions, the control to output transfer function in open loop. So here we have the different parameters of our circuit. Here we can see the three impedances that we have defined before, and this is the control to output transfer function with EMI filter GET, and here for comparison we have the control to output transfer function without EMI filter. With these statements we are plotting the body diagrams of both transfer functions, and these are several points that are printed corresponding to the transfer function GED. This is the control to output transfer function considering the EMI filter. So here on the right we can see in red we have the open loop control to output transfer function without EMI filter. We have seen this before in previous videos, but now in blue we have the transfer function considering the EMI filter. So we can see that we have this glitch here in this part corresponding to the resonance of the EMI filter, and also we can see that the phase of the control to output transfer function decreases very quickly in this part, and this is very important because this change of the phase of the control to output transfer function can affect also the operation in closed loop. Here we have several points corresponding to this transfer function, the one with the inclusion of the EMI filter. We can check this transfer function by simulation. We know that we can do it in 3 different ways, using the actual circuit, using the average circuit, or using the small signal circuit. In this case, we are going to use the small signal circuit, so this is much quicker, and we are adding here the two components corresponding to the EMI filter. Then we are injecting a perturbation on the duty cycle of 1 volt and measuring the output voltage here, VO. So with this we can obtain output voltage over duty cycle, which is the transfer function GD. We are performing this .AC analysis. And here we have the results from the simulation using LTSpice. So in solid line we have the magnitude of the transfer function, and in discontinuous line we have the phase. These are 2 points for comparison with the WinPython results that we can see here, so we can check that both the theoretical transfer function and the results from the simulation match very well. Let's analyze now the stability in closed loop. For this, we calculate the closed loop control to output transfer function. We have this block diagram that we know very well. We have seen it in previous videos. So from this diagram, by making null the perturbations on the input voltage and on the output current, we can obtain the transfer function corresponding to the output voltage over the reference voltage. So we obtain this equation here, and we know that the important function here is the loop gain, which is expressed with this equation and is the one that we use to study the stability of the converter. In principle, we can think of using the same PI compensator that we have used in previous videos. We have calculated this PI compensator for operation without EMI filter. So we did the calculation with this frequency for the zero of the compensator, and then we obtained these values for the capacitance and for the resistances of the compensator. We have seen that this circuit operates well when we have no EMI filter at the input. So let's analyze now what happens when we add the EMI filter. Here we have another script in which we have included also the response of the compensator here, CP, the gain of the sensor, which is equal to 1 in this case, and this is the loop gain T with EMI filter, and here we have the loop gain T1 without EMI filter. So here we are plotting these loop gains. In red we have the loop gain without EMI filter, so we can see that as in the previous videos we have a stable system and the phase margin is something like 30 degrees. But now pay attention that with the EMI filter we get an unstable system, because we are reaching here minus 180 degrees, while the gain of the loop gain is higher than 1. So this is clearly an unstable system. And this situation comes only for adding the EMI filter at the input without changing anything else. To have this kind of unstable system is not a common situation, so to be sure we are going to investigate this a little bit further by plotting the Nyquist diagram of the loop gains in both situations. Here we can see the Nyquist diagrams. It's very easy to plot these diagrams from WinPython. Here we have an excerpt of the script. we are using this function here, Nyquist plot, and then we can see on the left the loop gain Nyquist diagram without EMI filter. So we can see that the point -1, 0 is here and is out of the Nyquist diagram, so the system in closed loop is stable. However, when we plot the loop gain Nyquist diagram with EMI filter, we get this diagram here, and we can see that the number of encirclements of the point -1, 0 is equal to 3. So we are getting clearly an unstable system. Note that our original system is stable, so it has no poles on the right half plane. So for the closed loop system, we have at least 3 poles on the right half plane, and this makes the system clearly unstable. Let's check this by a couple of simulations. First, using the average circuit. As shown here, we can see the average circuit without EMI filter and operating in closed loop using the compensator. So here on the right, we can see how the output voltage stabilizes and get the output corresponding to 5 volt. However, when we add to the same circuit the EMI filter and run the simulation again, we can see that the output of the compensator increases and increases continuously, so the output is not converging and we are not getting the correct value for the output voltage. And now let's see what happens if we use the actual circuits. Here we have the complete buck converter operating in closed loop. Here is the compensator. We are using a limiter here at the output, as we have seen before. And then here we can see the output of the compensator and is stabilizing to a given value, and also the output voltage is getting the correct value of 5 volts. But when we simply add the EMI filter, as shown here, to the same circuit and run the simulation again, we can see how we get these oscillations at the output of the compensator, and also the output of the converter oscillates and is not getting a stable operation. So this is really important because only by adding the EMI filter, we can make our converter unstable. If we do not take the EMI filter into account when designing the closed loop operation of the converter. In a future video, we will see how to solve this issue. And with this, we get to the end of this video. I want to thank you for watching the channel. Please let me know if you have any comment or question, and I hope to see you in the next video. Goodbye now.